Hello, everyone. I'm Othmane, and I am here today with Ihsane, representing QuantCube Technology. And we're excited to share our project that we have been deeply involved in, which is the tracking of urban growth development using satellite data. And today, this is the structure of this presentation. I'm gonna give you a little introduction of QuantCube. Then I'm gonna dive a little bit into more details of the urban growth index that can be very related to what Sebastiano just showed. Then we're going to see some applications here we have a little focus on India, and then the conclusion. So QuantCube Technology, it's a fintech based in Paris. We have a large data coverage and a data lake containing over 15 billion different data points. It can be text data, geolocation data, geospatial and structured data. And we use artificial intelligence to make this data more valuable and to give and deliver real-time macroeconomic insights ahead of the markets so that we can help our clients, institutional investors, to build their optimal investment strategies. So we have built a whole expertise around computer vision, NLP, econometrics, finance, and economy. As you might tell, that in QuantCube, we are interested in economic index like GDP, commodity trade, port congestion, etc. And one of the indexes that we're interested in is construction. Thus, this project that we have built, because it can have a lot of economic use cases. So the urban growth index that we have built can be seen as a tool of innovation and impact, because it can help us measure development in its large meaning. It also can help have an idea on the growth in some sectorial activities, seeing some cities that really strongly related to a specific industry. Also, more buildings means more people. So there is more water consumption, electricity consumption, oil consumption, etc. And on the right screen of this slide, we can see the Indian case where I have plotted the GDP of India, and in green, I'm sorry, and in light blue we see the urban growth index that we have built in QuantCube. We aggregated the data of the 10 cities we have tracked, and we see in last 7 years that we have 18% growth in India. We also found that the urban population has increased during the same period of 14%. So there is an explanation of this 18% growth that we have detected thanks to our index. So now I'm going to dive a little bit into more details and talk about the main subject of this presentation, which is the urban growth project. But before that, I want to give you the existing solutions that has been used before to track the urban growth. So there are some traditional solutions with land use surveys, aerial photographies, and ground-based surveys. So this is the pre-satellite era. Then there is the solutions using satellite data, like VIRS night data, which is night data, Esri and ESA land cover. So all these existing solutions might have some problems like scalability. It can also be very costly and demand a lot of manual work. And for the satellite data, the frequency of availability of the data, it's quite large. We have annual updates, and the resolution for night data, it's 1 kilometer. And for the Esri and ESA land cover, it's 10-meter resolution. And in QuantCube, the approaches we have developed uses Sentinel-1 and Sentinel-2 data for the low resolution part. So here we have a distinction between low resolution and high resolution. The first one I said, it uses Sentinel-1 and Sentinel-2 data that Sebastiano explained just before in his presentation. And the index we're going to build based on this data going to be quarterly. So we're going to have the updates each 3 months. The resolution here, it's 10 meter, and the historical data starts from 2016. And in case we're interested in a specific region, we can detect here in red, for example. So this is on a large scale level. This is where we use the low resolution Sentinel-1, Sentinel-2 data. In red, it's the new buildings that have been built. And since it's cost efficient to start with this low resolution approach, in case we're interested in a neighborhood, we're going to use a higher resolution data with a Pléiades satellite. So it's data, it's a data with spatial resolution of 15 centimeters. So the frequency here, it's not defined since the data is on demand. And here we see the picture that is very granular, and we can see the buildings very precisely. Okay, so now I'm going to present how we did all this. I mean, the technical pipeline. On the left side of this slide, we see we have the low resolution approach using Sentinel-1, Sentinel-2 data. And this is the image, the result of our pipeline. In red, we see the new buildings that has just been built. And we're going to have zoom in this area and use Pléiades images that are more with a higher resolution in order to do a segmentation and a classification of the buildings. And also we can compute the volume of the buildings. So with the first approach using low resolution data, we're going to have the estimation of urban growth in 2D, so it's a surface. But thanks to the second approach, we can also have the estimation of volume and in the urban growth in the height. So here I'm going to dive a little bit into the first part using Sentinel data. And here I'll be presenting only let's say, a sub-pipeline using only Sentinel-2 data. So historically, this project has been first built only using this data. And later, we added another sub-pipeline using Sentinel-1 to make the whole pipeline more robust. So this one is the one using Sentinel-2, which is the optical images. It mainly is divided to 4 steps, which is the download of the data, the pre-processing using cloud detection in order for us to find a solution to that, because on Sentinel optical images, Sentinel-2, if we have a cloud, we can see what's going on Earth, on the ground. So this is a problem with this data. The third and fourth step, it's the prediction using a deep learning model. And of course, the post-processing to generate a probability max that gives us the probability per pixel if the pixel is urban or non-urban. On the right side of this slide, we have the S2 cloudless, the detection of the cloud. And on the bottom, we have the results of the S2 pipeline. On the left, in the middle, it's the benchmark ESA, which is the ESA world cover that we're going to be compared to. And on the right, it's the ground truth OSM, which is the data that we use to label and to train our model. Here, as you can see, we have zoomed in a specific region. This is Paris, and we have zoomed, and we can see that with ESA land cover, a garden in a house is not considered as an urban area, but thanks to the urban growth ContCube pipeline, the garden is going to still be considered as a part of an urban area. So that's it. I'm going to move to the second sub-pipeline, which is going to be the Sentinel-1 approach. So again, this pipeline is based on radar data, because as I said earlier, the optical images might have the problem of the clouds, and thanks to radar, we can go through these clouds and see what's going on the ground. So this pipeline, it's started with the download of this data, then the pre-processing using a deep learning model, sub-CNN, and we can see the picture on the left. It's the raw image. So as you can see, there is a lot of noise there, and we use it to smooth it a little bit and using a deep learning model to obtain the picture on the right. Then there is the rest of the pipeline that uses a prediction using a machine learning model, all classical one. Then, of course, the post-processing. And these are some results of this Sentinel-1 pipeline. So here we have the segmentation of over Amsterdam, Mexico City, and Jaipur. So now I'm going to move to the other parts, which consist of doing an aggregation of these two sub-pipelines, so the Sentinel-1 and Sentinel-2 pipelines. Each one of them gives us a probability mask, and we merge them using some specific functions. And one important thing that I want to insist on is that, as I said earlier, we help our investors build their investment strategies, and images are not not valuable to define a strategy. So we need to translate them to a time series. And this is what we see on the bottom of this slide. So it helps us see the evolution over time of a specific area of interest. And I've put some results here with the different metrics, but overall, the S2 pipeline itself, it yields a convincing result against the ESA world cover. Seeing the F1 score, we beat the benchmark on most climates and continents. And our pipeline is less sensitive to the presence of vegetation and also cloud, obviously, etc. And some of the potential developments are, of course, going to be using some more sophisticated deep learning models and having a bigger data set to train our model, and probably having one pipeline that uses from the beginning Sentinel-1 and Sentinel-2 data. Now that we have seen the low resolution approach that gives us the urban growth on a large scale, we might be interested, as I said earlier, in some specific areas, and thus we're going to be using a higher resolution data, and I'm going to yield the floor to Ihsane to present this part for you.
So for the high resolution pipelines, it's a very classical pipeline, which means we start by downloading images. The payed images have a 50 centimeter resolution, as Othmane said before. And after pre-processing steps, we give the data to a deep learning model, creating a building classification map where we have the buildings. The buildings here in red that are segmented against the background. And we need to keep in mind that with this pipeline, we have three main outputs. The first one is this one, the building classification map. The second one is a building type classification, where the building is classified between an industrial, residential, or commercial type with another proprietary deep learning algorithm. And since our investors are very interested of any urban change, but most cities and the most urbanized cities, like Sebastiano explained in the previous presentation, are not only growing vertically, horizontally, surfacically, but also vertically, like adding floors on a building, for example. And that's why we have a third output, which is the digital surface model, where every pixel on the image has an estimation of its height, which gives us, combining with this building classification map, a volume estimation of the urban area targeted. We have very good results overall. We have 84% of accuracy of building segmentation. The validation has been done on a proprietary database, but it comprises all of the continents and very diverse regions topographically, like deserts or mountain regions. And also our other deep learning algorithms targeting the building type classification has a 70% of accuracy, for example, for the industrial type classification.
Thank you, Ihsane. So now we're going to move to see some applications. And we're going to have a little focus on India, since it's an interesting case that we have seen in our data, because India have grown so much in the last few years. But our indicator is available, it can be available worldwide. Here I'm going to be presenting for you only the ones, the results on India. So I've took some screenshots from our platform. Here I've put some video to see, the evolution over time. We have the color code, so from white to red. Here it's, I've chosen two random cities. It's Unnao and Jaipur. So yeah, we can navigate on the image, the satellite image, and see, the image visually, the buildings that have been built. And on the right, we can see, for example, Jaipur, that it's a city that is growing on the left of the city, on the left side of the city. And again, this is the time series that shows the evolution over time of Jaipur. And we also might be interested in, as I said, a specific area. So probably, Ihsane, if you want to talk about this part.
So for the high resolution part, as we said before, we target a specific neighborhood where we see significant change with the low resolution pipeline. This is a neighborhood in Jaipur, India. So for each date available, so we have 2012, an image in 2015, and an image in 2018. We have combined the building classification map with the digital surface model, giving us the volume estimation of this neighborhood. And we can see that we have the 69% growth overall between 2012 and 2018, but more significant growth between 2012 and 2015 that has slowed down between 2015 and 2018. But our investors are also interested in a more precise analysis of those changes. And that's why we also output a change map. So between 2012 and 2018, we can have a change map looking like this. So all the green buildings are the new built buildings, and the light blue buildings are the destroyed buildings. Because our investors would be interested if a new type of building has appeared in another type of area, for example, a commercial building created in a residential area. And now that we have seen an overall overview of our project, we can delve more into the applications. Like Othmane said at the beginning of the presentation, by aggregating the surface of different cities in India, we can have an approximation of the GDP, especially in the pre-COVID period. But on a more micro scale, and doing something that we know very well how to do in QuantCube, which is merging different data sources. So the building classification with the telecom data and the textual and script data, we can give investors a very valuable insights on the real estate market, and so the real estate investment, and also on the risk and how to monitor risk for specific assets. So I hope I give you a good idea of what we do in QuantCube and of this project with Othmane. Thank you for your attention, and don't hesitate if you have any question.
Thank you so much.
Okay, thank you very much on this nice presentation that complements very well the previous one. Are there any questions from the audience? Not yet, but I'm going to start with a question. On one of your few last observations, when you said that you track the changes in the, let's say, the construction, of course, it can be quite useful on the to track, let's say, the evolutions. But let's say, suppose that you have a building that doesn't change apparently, but for example, you have one additional floor. Because I don't know, the regulation has changed on the now you can increase all the buildings by one floor. How are you going to get this increase? Because apparently on the ground it will be the same building, except that okay, you have one additional floor. How could you track this this changing, which is not that obvious change compared to the one in which you have nothing and then a building? So this one is clear, but you have one building and then another building on top of the first one. How could you capture this change?
So, as I said, with layered images, because they are stereoscopic images, we can calculate what we call a digital surface model. And this model gives us for each pixel of the image a height estimation. So we can compare two different dates, the height of the building between the two different dates, and see that there has been a significant change and the height that corresponds to a floor. Okay.
And I have another question. In one slide, you refer to a benchmark, and you said that you have you're able to beat the benchmark. But could you just, perhaps I missed it, remind what your benchmark is?
The benchmark was the Ihsane uncover.
Okay, so, uncover. Okay.
It was the Ihsane, and it was more for the large-scale approach using Sentinel-1 and Sentinel-2 data.
Okay. Perfect. Okay, thanks.
Because for the high-resolution data, we have a proprietary database that has been manually labeled on layered images on all continents. And that's what we compared our results and validated our results.
Okay. And compared to what was presented about China, to what extent is your technology complementary from the presentation that was made by the paper on the floor space in China?
Well, first, our pipeline is global. We're not focused only on China, but we have also very good results on China. And also, I think it's more precise because we have the high resolution part. So we go on a very precise scale where we can see very precisely the surface and the height, and the results are very precise and validated with the reality. So, and I didn't see that on the other presentation, but maybe
Okay, I see that Sebastiano is still there, so perhaps it will be interesting to react. So please, sorry, I interrupt you.
Yeah, I was just gonna say that it's quite similar, to be honest, and complementary, because what Sebastian have shown, I mean, it uses the same data we use on the low resolution, so Sentinel-1, Sentinel-2. But the part that Ihsane just presented, I mean, it uses player data, which is, I mean, not free data, so it's costly compared to Sentinel-1 and Sentinel-2, but it helps us goes and dive a little bit into more details and see exactly, I mean, it's 15 centimeter data, so it necessarily gives us a better granularity and a better estimation, but it can be more, I mean, costlier.
And also we don't have as much history from this satellite because it's an undimmed satellite, which means we have few images for specific areas and not the whole world necessarily.
Okay. Sebastiano, if you want to intervene.
Right. I mean, that's exactly what I meant with there is remote sensing techniques that do much better than what we do, obviously. But what we do is we work on the scale, right? And exactly, you need to be. So if I understand that correctly, you decide that you're interested in a certain area, and then you buy this patch of satellite image, of high resolution satellite.
Yes,
imagery,
exactly.
Right?
Exactly.
Right. So and for us, I mean, we want to do research. We want to have long-running panel data. I mean, even from a computational point of view, it would be difficult to do this on scale, right?
Yes. Yes, it's very intensive, and we are lucky enough to be a part of a consortium that includes the CNES, which is the French Spatial Agency, and it gives us access to their cluster. So we have we have enough resources to train our models and on such a large area of data and such a precise scale.
But of course, it's going to be, I mean, it's going to demand more resources compared to the low resolution because, I mean, 10 meters, we have 2015 centimeters in, I mean, which means 1 pixel in Sentinel-1 is going to be translated to 2000 pixels in Pleiad. So necessarily, if we want to cover the same area, it's going to be, I mean, very, very heavy as a data to use. And of course, it's probably not very, I mean, scalable. This is why we have a focus on specific regions.
Okay, interesting to compare the two approaches, which indeed are very complementary. Any last question before we switch to the presentation from OECD? No. So I thank you again for this presentation, which indeed was very nice and very complementary from the previous one. So it can give some interesting insights about the frontier, about what can be done with satellites.